Hello, everybody. My name is Itamar, and I'm agronomist in the R&D department at Netafim. And today I'm going to talk to you about irrigation monitoring by sensors. So what we're going to talk about today is all sorts of sensors that we use for irrigation scheduling and monitoring, like atmospheric sensors, soil and plant sensors, system sensors, and about how do we install them shortly, and how do we use sensor for irrigation scheduling. So first of all, we need to understand what is monitoring. So monitoring is basically everywhere. In the image that you can see now is the dashboard of your car. And there you have a lot of information about how much fuel do you have, and if the car is getting heated, or what speed do you ride on. And this is very important to know if you're driving on the right velocity, and if you have enough fuel, or do you need to stop and refuel. And the same is actually for irrigation and crop monitoring. You need to keep updated on the status of your field and your crop. So why do we basically need to irrigate? So we have a plant or tree, and in those leaves of this plant or tree, we have a lot of tiny factories that manufacture sugars, which are the building blocks of the crop, of the yield. And in order for those small manufacturing machines to operate, we need several things. We need light, we need CO2, and of course we need water. And the water is something that we can adjust and control. The light and the CO2, we cannot control them. So we can control the amount of water that we apply for the water in order for those tiny plants to keep on running and producing yield. So about crop monitoring, the advanced farming technologies that we have today allows the farmers to achieve much higher yields than they used to be. And in order to get the full yield potential, the farmer needs to constantly aware of the crop status, and to see that it's developing well, and to see that it's irrigated well. So this is the reason why he needs some kind of crop monitoring to assist him with that. So if you look on the plant in the field, we can see some kind of soil plant atmosphere, water continuum, that it's a line of water that starts from the soil, goes through the plant and back to the atmosphere. This water continuum is the thing that makes the water flow from the soil to the atmosphere through the soil, through the plant. So we can actually monitor each one of those segments in order to see that the cycle is going well. So we can monitor the soil to see if there's enough water in the soil. We can monitor the plant to see if it's under stress or not. And we can monitor the weather and the environment in order to see what's the water demand in the environment, because this is what will determine how much water the plant will consume. And at the end, our goal is to close the loop and to give irrigation according to the plant requirements. So there are a lot of advantages in using soil sensors and plant sensors, and all sorts of sensors. We can get continuous measurements, and not just when we visit the field. It's continuous 24/7. We can monitor the irrigation system performance to see if we actually applied what we intended to do. We can monitor the crop development to see if it's on the right pace. We can identify over and under irrigation, set threshold for irrigation, and we can give efficient and precise irrigation, and we can adjust the irrigation according to the weather conditions of the surroundings. But we have some disadvantages of the soil sensors over other sensors. And first of all, the cost. It costs to buy them. You need to install them, and sometimes it's not that easy. Some of these sensors need the interpretation of the results, and all the sensors actually measure just in one point. So if you have a large field or orchard, you actually measure in one point or one tree, and it's not always represents the entire field. And we have several types of sensor. We have the atmospherical one, soil, plant sensors, system sensors, and of course remote sensing that we'll not talk in this session. So if we start with the basic, which is atmospherical sensors, it's basically a weather station. And weather station can give us a lot of information, as you can see here on the list, like the temperature, the humidity, radiation, the wind, and a lot of information that helps us not only for irrigation, but also for other agronomic practices that we need to do. And in Netafim, we are using the Davis station, which is very cheap and gives you a good value for money, and you can place it everywhere. It's standalone, and you can get all the information online from this weather station. So what can we get from the weather station? We can do irrigation according to the ETO, the evapotranspiration, the reference evapotranspiration that the weather station can calculate. We can have the wind speed and direction if we need to do some spraying, accumulative heat and the cold units that we need to crop development, GDD, which is growing degree days, if we want to know the development of the crop, and of course the rainfall, which is very important if we need to know how much to irrigate after rain events. And in some cases, we can have the full weather service like we have in the NetBit platform at Netafim, which is a global coverage of weather service, which is model-based, and it can give you historical weather data according to your location, and you can see what's been the condition in the past 20 years. You can get the current environmental conditions, and you can also get the forecasts, so you can know if there's a rain coming or a heat wave, and you can plan your irrigation according to that. Now let's talk about some soil water content terms before we jump into the soil sensors offering that we have. So we have three types of water contents which are very important to us to know. First one is the saturation. Saturation is when all the soil pores are filled with water and there is no air. And this situation is very short-term, and it is following massive irrigation or rain. After that, after some of the water has drained, we are coming to the fill capacity, which is all the big pores of the soil is drained, and all the water is being held in capillary forces in the soil. Another thing that we have is the wilting point. And the wilting point is where the water content is very, very low and the plants cannot extract any more water, and they actually wilt and die. And this point is what we want to avoid and stay away from this point, and I will explain about it later. So if you want to see the graphics of that, this is the three water contents that we have. The saturation, you can see that all the pores are filled with water and there's no air. When we are in fill capacity, there's some water and some air, and some of the water are actually available for the plants. When we are in wilting point, you can still see that there are some water inside the soil, but they are not available for the plants. The plants cannot use them because they are tied in a very narrow voids of the soil. So if we are talking about what's available for the plants, we are talking about the total available water, TAW, which is defined as the amount of water between fill capacity and wilting point, and it's for a given soil, and I'll give you some examples for that. And as I mentioned, in irrigated crops, not all the total available water are actually used because we don't want to come near the wilting point. So actually, we can define the readily available water, or RAW, which is the amount of water between fill capacity and up to 50% of fill capacity to wilting point, which is basically we are reducing the amount of water from the total available water. We don't want to come near the wilting point because it will be harmful for the plant, and I will explain about it. So here in this table, you can see the 12 soil types that we have. And this table is from the FAO, and you can see the different types of soils, from sand to clay, and you can see that there are the soil water contents. You can see the fill capacity and wilting point, or permanent wilting point. And you can see that for different soils with different values for fill capacity and wilting point. And if you go from sandy soils to clay soils, the water content of fill capacity and wilting point are increasing because the soil can hold much more water. And on the second from the left column, you can see the total available water, how much water are logged in terms of millimeter per meter of soil are logged in each one of these soils. And you can see that sandy soils hold much less water than medium soils or heavy soils. And it's basically the if you can take the fill capacity and reduce the wilting point, it's exactly the number that it's written under the total available water. And if you look on this graph, this is just a graphic numbers of the table that you saw before. You can see that the total available water of sandy soil is much lower than for clay soil. And here you can also see the allowable depletion that we allow, which is defined as 50% or sometimes even less. And this is the readily available water that we have for the plants. So we are not talking about all the total available water between fill capacity and wilting point. We are talking about only available water between fill capacity and the allowable depletion that we can get. So in order to understand the differences between different soils, we have the retention curve, which is different between different soil types. And you can see that the retention curve has two axes. We have the y-axis, which is the water potential, which tensiometer measures this axis, and we have the x-axis, which is the water content, and we can measure it with water content sensors. And you can see that if we reduce the water content, the water potential is increasing, which means that the plant will need to invest much more energy in order to extract water from the soil. And you can also see that for the value of fill capacity in the water potential, you will get the same value, but it will be different value of water content for different types of soils. And this is very important to understand. So what are the available soil sensors that we have? We have tensiometers that, as we explained, are measuring the soil water potential or water tension. And we have sensors that measures water content, and they are measuring in a point or profile, as we'll explain in a second. We have salinity sensors and soil temperature that will not talk in this presentation. So tensiometers. Tensiometer measure the water tension in the soil or water potential. Higher tension means less available water for the plants. And the tension is, like I showed you in the retention curve, is very similar for a wide range of soil textures, which means that if we are having a value of 30 centibars, which means around fill capacity, it's the same for almost all the soils. And you don't need to know the exact value of water content for each one of the soils. So it's very easy to interpret the values of the tensiometers. And here in Netafim, we are using the Irrommeter tensiometers, which are very good tensiometers. They are very robust and very easy to install. The tensiometer is actually a hollow body with different lengths between 30 and 90 centimeters, with a ceramic tip at the end and a filling cap at the top. And you just need to fill this sensor with water and install it in the soil. And you will have, as you can see on the right side, you'll have a transducer that converts the tension into a current, an output of voltage that we can actually read with our systems. And the values of the tensiometers are very easy to interpret. And you can also find some analog tensiometers with a gauge like you see in the image. And you can see the different ranges of saturation and fill capacity, and where you need to irrigate in each one of the different soil types. So the tensiometers are very easy to install. The values are very easy to interpret, and they are pretty much a cheap sensor, and they are widely used. The problem with the tensiometers that they have low range of values, so they cannot be used for stress crop like cotton and vineyards, because we are talking about much higher water stress that the tensiometer just can read. It's out of its range. And it's very subjected to temperature effects, as I will show in a second. It has a lot of maintenance because it's filled with water, and you need to once in a while fill the tensiometer with water, and it measures only one depth, so you need 3 of them in order to measure the entire soil profile or the root zone. So if you look on that graph, you can see the different depths. Usually the red one is the lower one, it's at 30. The green one is at 60 centimeters, and the deeper one is at 90 centimeters. And you can see that between irrigations, the water tension is increasing. And after irrigation, all the values drop down to around 0, which is saturated soil. And you can see a lot of curves, which are basically results of the temperature, because the tensiometer is very sensitive to temperature. The other types of water content of soil sensor is the water content sensors. So the water content sensors measures the volumetric water content in the soils. The measuring principle is the dielectric constant that the soil have and being measured by the sensors. The measurement range is usually between 0, which is totally dry soil, and 100, which is totally saturated soil. And for different soil textures, there are different water contents for saturation, field capacity, and wilting point, as I showed you in the previous table of the different soils. And there are point sensors that measures only one point in the soil, and there are profile sensor or multi-depth sensors, and I'll show you some examples for that. So how those sensors actually work? They are working on the principle of the electric constant, and air and soil do not able to store any charge, but water does. And for that, if we place a sensor in a dry soil, it will don't show any response. But if we add some water, so the sensor will do some calculation, and it will output the some kind of current that can be translated into volumetric water content. So those sensors measure the volumetric water content in the sensors surrounding in the soil in a volume of about 250 to 1 liter, and it very depends on the soil, on the sensor size. And for the profile measurements, few sensors are installed in different depths. If you want to measure the entire root zone, you need to install few of them. So Netafim is using the SM150T sensor by Delta T. It's an excellent sensor that measures between 0 and 100%. It can be used for all types of soils, and it can be also used in greenhouses for soilless beds, for coconut and other planting materials. It's very sensitive, it's very accurate, and it's very robust, and it's not sensitive for salinity, so you can use it in a lot of scenarios. The problem is with the soil sensors that you need to interpretate the water content, and each soil type has different value for saturation, field capacity, and wilting point, and you need to adjust the threshold for irrigation according to each soil type. And you have the different soil types and values of field capacity and wilting point in this table. And later on, I will show you an example how to calculate the refill point of each soil for irrigation monitoring and scheduling. So here in this graph, you can see the difference between the water content sensor, the SM150, and the tensiometer. So the water content is in the green and red lines, and the tensiometer is in the brown and purple. And you can see that once we have irrigation, the water content just increases and the water tension just drops down. And after that, you can see the reduction in water content because of plant consumption, and you can see the increasing of water tension. And then the second irrigation, and the water content increases and the water potential drops down. And also we have profile water content sensors that it's actually like a pole with several water content sensors inside of it. We have several measurements points along this pole, and you can get a lot of information about water flow and root uptake from different soil layers. And here in the Netafim, we're using the NetaCap sensor, which has 6 points of measurements of water content and temperature, and another point of temperature measurements in the cap that actually measures the air temperature. So this is the sensor. You can see that it's a pole. It's a multi-depth capacitance sensors, and it has several lengths between 0.3 and 1.8 meter long. It has up to 6 measurement points of water content and temperature. So here in this table, you can see all the offering that this sensor has, from 20 centimeters to 180 centimeters. But we usually, for open field and orchards, use between 40 and 80 centimeters. This is the vast majority of sensors that we use. And here in this graph, you can see a lot of information that we can get from this sensor. You can see all the irrigations in the different depths, and you can see where the water is being logged, and you can see the drainage, and you can see how far the water has entered the soil, and if the water has reached the deeper layer or not. And you can actually see where the root zone is located. So if you look on the most upper graph, this is actually the 80 centimeter water content, and you can see that the water content is very high during the season, but at the end, all of a sudden the water content is dropping down, and this is because roots has developed and came to the 80 centimeters soil depths and started to extract water from this layer, and this is the reason why the water content is being reduced over there. So about water content sensors, they are very accurate, and it basically depends on the brand. They have wide range of measurements, so you can actually use them in stress crop like vineyards. It's maintenance free, so you can just place them and forget about them. You don't need to fill any water. And it can also work in soilless beds, in greenhouses and others. The problem with that is some of them are very expensive. Some of them are sensitive for salinity. You need to do installation of that. And if they are large soil sensors, so you need to dig a trench for that. And the values need to be interpreted and related to soil type, because as you saw in the table, different types have different values for fill capacity and wilting point. So you have to know your soil. So let's do a quick checkup point to this presentation so far. So tensiometer are widely used but needs maintenance and not suitable for stress crop. Point water content sensors like the SM150 are very accurate but needs installation. The NetaCap sensors can give good information about the entire soil profile and water distribution in the soil. And all the water content sensors are value dependent and needs interpretation. So let's move on to the other family of sensor, which is the plant sensor. So plant sensor actually integrates the water status in the soil and the measure what's the plant feels. The plant sensor measures the plant response to water. Some of it is directly and some of it is indirectly. The plant sensor can indicate any water stress and growth rate of the plant. And the available plant sensors that we have is dendrometers, fruit size, and leaf temperature, as I will show you in a second. So the widely used plant sensors are the dendrometers, and they measure the changes of the tree trunk or plant stem diameter. And from those sensors, we can actually extract two indicators, which is very important for understanding the status of the plant. So first of all, we have the MDS, which is the maximum daily shrinkage. Higher MDS means higher water stress, and I will show you it in a second. And the second term that we have is the trunk growth rate, and higher trunk growth rate indicates good water status. So if we go to the next slide, here you can see actually what the graph of the dendrometers looks like. So you can see that during the day the trunk is shrinking, and that's because the plant is losing water. And you can see that if the plant is under more severe stress and has less irrigation, the MDS is much higher, which indicates much higher stress. And the second one is the growth rate between 2 days. And you can see that if the water status of the plant is good, you can see that we can get higher growth rate between different dates. And that means that the plant is developing well. And another sensor that we have is fruit size, and it comes with different sizes, and it measures continuously the fruit size, and it can indicate if the fruit is developing according to planned, and if we need to irrigate more, because sometimes if we do under irrigation, the fruit will not develop as it should, and we need to increase irrigation. And here you can see also stem dendrometers for cotton, and you can place it also on corn and other plants, and it can give you good information about the crop development. So it's not only for tree crops. And another sensor that we have that can be used for several reasons is leaf temperature, which measures continuously the leaf temperature, and the leaf temperature is correlated to transpiration rate. Higher temperature indicates lower transpiration and possible water stress. And if the temperature is lower, that means that the plant is doing transpiration, and the plant leaf temperature will be lower. That sensor is good for vineyards and other stress crop that we need to manage the stress on the plant. So plant sensors are very useful and give a lot of information about the plant water status. It's not sensitive to any soil effect, and usually they have little maintenance. The problem with the plant sensors is that the values often require interpretation and understanding of the results for each one of the crop and each one of the growing stages. So you need to know how to interpret the results and how to manage your irrigation accordingly. So if we look on that graph, this is the seasonal trend of a dendrometer, and you can see that in the early stages, you can see the tree development, and you can see that the trunk is increasing. But after that, you can see that the trunk is not responding anymore, and the tree is investing most of its energy in fruit size increasement. And here you can see that we can put together dendrometer and tensiometer, and you can see the development of the trunk. And you can see that when the soil is at high potential, and you can see the high bars of the tensiometer in red, you can also see the response of the dendrometer. You can see a lot of shrinking during that period, and I will show you much exact example. You can see here that every time that the water potential is very high, and this is a tensiometer, the tree responses with much deeper MDS, and after irrigation, the MDS comes back to the natural situation. And you can see that every time that there's some kind of a stress in the soil, the tree responded accordingly. And you can see that also with water content sensors, every time that the soil water content is decreasing, the plant is responding with higher MDS. And every time we irrigate and the water content is increasing, the MDS is back to normal values. So let's do a little checkpoint. So plant sensors actually feel the plant itself, but the reading needs to be interpreted, and the plant's sensor only represents few plants out of many. So it's very important to place the sensor at representative trees or plants, and to put few of them across the plot in order to represent the entire field. And we have another type of sensor, which is irrigation system sensors. We have inline water meters that measures the water flow in the laterals. And you can actually compare if we gave the exact amount of water as we intended. Sometimes we have irrigation problems like water loss or pressure loss, and we don't actually give the entire amount of water as we plan to. And we have inline pressure sensors that can monitor if we are operating in the exact pressure that we need, because if we drop the pressure too much, the irrigation efficiency will not be as planned, and the meaning of that is less irrigation as we planned. So here on this graph, you can see water content response, and you can see in the blue bars the water meter. And the higher the bar of the water meter means higher irrigation amount. And you can see at the middle irrigation, you can see small irrigation that didn't penetrate to the deeper layer of the soil, so you don't see the deeper blue graph sensor response. And if you have higher irrigation, you can see that the deeper soil is responding. So a brief about installation guidelines. It's very important to install the sensors correctly. So the sensor should monitor the root zone activity, and the common installation of sensors is we usually install 3 sensors in 10 to 30 the first one, 40 to 60 the second one, and 70 to 90 centimeters, but it could be changed according to the plant root zone distribution. But this is the general depth that we install, where the shallow sensor usually is used for irrigation trigger, the middle one for the irrigation depth tracking. So if not enough water reached the medium sensor, the middle one, that means that we didn't irrigate enough. And the deeper sensor is usually there for monitoring if we are not doing any leaching or over leaching of water below the root zone. And the common practice is to put the shallow sensor about 10 to 15 centimeters from the dripper along the drip line. And the deeper sensors can be placed next to it. And the thumb rule is that good installation gives you good data. And if you don't practice good installation, you will get bad data, and all of your decision will be actually wrong because you didn't install the sensors as you should. And just to give you how to an example how to install the SM150, so you place them next to the dripper in 3 depths, and they represent the entire root zone of the plant if it's tree crops or open field. So how we can use the sensor for irrigation scheduling. So first of all, we need to find the field capacity of the specific soil that we have, and I'll show you how to do it. We can look on the sensor trending, the reading trend, and we use the upper soil sensor for irrigation trigger, and we use the lower one or the middle one for irrigation quantity. First of all, we need to find our field capacity with the soil sensor. So if we look on the trend of irrigation, and you saw that in previous examples, you can see an increasing water content, which is because of the irrigation. Then you will see rapid decrease in water content, and this is the drainage. It's the transformation between saturation to field capacity. And if you draw a line between the drainage and the very horizontal line of the sensor, this is the field capacity point, which is, in this example, it's about 90%. So this is the way to find the field capacity for each one of the soils. So this is something that you need to do only once, and after that you know your field capacity at that specific soil. So once you know your field capacity, now you can find your threshold for irrigation. So you can estimate your wilting point from the table that I showed you previously. And now we need to set the allowable depletion. And as I told you, it's up to 50% of the total available water. That will be our refill point. And we need to maintain water content above the refill point. So every time it comes to refill point, we need to open the irrigation. So now we'll do a short calculation example. So let's say if I have a soil that the fill capacity is 30% and the wilting point from the soil table is 60%. So that means that I have 40% total available water. But since I don't want 40%, I don't want to come near the wilting point, I will set a threshold of 40% out of the total available water. So I can calculate the and multiply the 40% in 40%, which is the allowable depletion, and the new threshold is now 24.4%. So this is actually 24. So this is the new threshold for irrigation. So every time the water content reaches the 24%, I apply irrigation. And I'm looking on the upper soil sensor. Every time the upper soil sensor reaches 24%, I apply irrigation. And you can also look on the trend of the soil sensor. And if you can see the decreasing or a negative trend, that means that we are in under irrigation. So we need to increase irrigation or increase the irrigation intervals. And if we see the opposite, we see the positive trend, that means that we are over irrigating. And we need to reduce the amount of irrigation or to switch the irrigation intervals. So for summarize this presentation, sensors, all of them, soil, plant, atmosphere, helps us know and feel the field and the plants. It can help us do crop monitoring and can alert any irrigation problems that we have in the field. Crop monitoring can assist with irrigation scheduling, and we can plan and do the irrigation based on this, the sensors reading. And the crop monitoring can increase water productivity and saves us a lot of water and money. And good practice of installation, the right set of sensors, can be beneficial for the farmers. So you need to use both soil sensors and plant sensors and weather sensors in order to monitor all the components in your field in order to make the right decision about irrigation. So thank you very much. And if you have much more questions, you can contact me in my mail